Well, good morning, everyone. Thanks for coming out on this cold and snowy weekend. Maybe that's the reason you came out, to get away from the cold and snow, right? So, how many students do we have from New Haven today? All right, great. West Haven? How about any from Hamden? Yay, Hamden, that's where I'm from. Guilford? How about Massachusetts? Anyone make it from Massachusetts or New York? Anyone from out of state this week? No out of staters? Everyone's from Connecticut this week. Well, thanks again for showing up for the start of Science Saturday for the spring semester. I'm glad you could all come out today. We got a real treat. A friend of mine, Professor Mark Reed, is going to tell us about his research today. We have an office of institutional research on campus that studies everything. And one of the things they study is where faculty come from. And so I have what my postdoc advisor told me is the Mutt pedigree. I did my bachelor's degree and my PhD at the same place. And then I worked in industry pretty much at the same place. And then eventually made my way to Yale. And the guys at OR said, Kurt, you're very unusual. I mean, there's only one other one like you. And when I was looking up his CV today, I found out that this is the other one like me. So Professor Reed did his bachelor's and PhD at Syracuse, the Orange Men, the other team that UConn plays, I guess, right?
I always root against the UConn. I root for the Orange Men.
And then he did something that used to be a lot more common, and I think has probably had a big effect on his career. He worked in industry. That doesn't happen so often anymore, but it really, I think, for me, it helped ground me in what I do, and I'm certain it has helped him make his research more responsive to society. And after that, somehow we got him to come to Yale, where he's been a force of nature ever since. And I'm a physical chemist, and so I don't overlap with too many of the electrical engineers, except when I need some help with designing instrumentation in my lab. But Professor Reed has got this dream of making electronics out of molecules, and that's happening. You've got your organic LED displays. That's sort of the first wave of this in consumer products, and it's really going to be a revolution. And he's sort of the father of this, right? So join me today in welcoming Professor Reed.
Well, thank you very much. Can you hear me? Good. All right. So it is a true pleasure to give this Science Saturday talk, because the reason I'm a scientist was when I was about 12 years old, I went to a Science Saturday at Syracuse University, and it turned me on. And it really showed me, and so I went to the first one, I loved it, and I kept going to them, and learned the fact that science is just not what you read in the textbooks, but it's a really vibrant profession and just tremendously interesting. So after I've stuck around Syracuse, and I went to school there. I got my undergraduate and graduate degree there. And then I went to Texas Instruments and started to wear cowboy boots and worked in the same laboratories that Jack Kilby made the first integrated circuit. And then eventually came up here to Yale. I'm in the electrical engineering department, but I'm actually a physicist. The reason I'm in electrical engineering is electrical engineering pays more. But seriously, the area of what I do, which is electronics, spans everything from chemistry to electrical engineering to physics and a lot of other disciplines. It's a big, wide discipline. Electrical engineering is the biggest profession in the world. There are more people in electrical engineering than any other profession. So then I came here to Yale and I started to make tiny things. And this scale bar that you see right there is a micrometer. And you kind of, till you don't have a good feeling for how big that is. So let me give you an idea of the size scale here. Take a hair from your head and look at how big it is. And it's about 80 micrometers across. So these little things, and here's a little bit of corporate graffiti that I did here, is at a size scale that's pretty hard to imagine. And in fact, modern transistors are about as big as the period at the end of that sentence. So I'm going to tell you a little bit about electronics and where it's headed and some of the fun things. When do you think the first computer was actually made? Anybody? 1940s, 1950s? Yeah? What do you think?
1967?
1967, yeah. In fact, there are a lot of computers made over the age. Here is the first computer. And it was mechanical. Done by a guy by the name of Babbage. Here's a part from his first computer that he made. Wasn't very smart, didn't do a whole lot of things. In fact, it didn't work very well at all because at the time they couldn't machine things very, very accurately. Well, in fact, a number of years ago, people tried to reconstruct it from his original diagrams, and it sits in the Museum of London, I believe. And it's a mechanical computer, and it works with gears and switches and things like that. And they actually do computations. And in fact, it works. But it's a big thing. That whole computer would fill up this entire room and would only be able to do a few things. It's actually a wonderful thing. There's a nice divide. That's what it looks like when it does it. So check it out if you're interested. It's a really neat, neat system. Okay. But then we wanted to start to get electronic. So in fact, the first transistor, or a transistor type thing, was actually invented here at Yale by a guy by the name of Lee DeForest. And it was something called a vacuum tube, and it was a vacuum tube transistor. It's a very interesting story, in fact. This guy, he was an undergraduate here. He was playing around in the laboratory. He actually got kicked out of Yale because he short-circuited the entire campus and blacked everything out. Well, they admitted him back a few weeks later, and he went on to become very famous and really was able to move the field forward in being able to use things that would look like a transistor. And so a few years later, people are actually able to make computers out of this. This is the first computer ever made that was electronic. And it was something called the ENIAC. And here's a picture of a part of the thing, and in fact, it roughly was the size of this room. And it could do all of 5,000 additions or subtractions per second, or 30 multiplications or 50 divisions per second. You can buy a calculator in the checkout line of a grocery store that's a factor of 10 more powerful than this thing for $1 today. Actually, what was most impressive, to do this, it had to use 18,000 vacuum tubes. Here's a little picture of a vacuum tube if you've not ever seen one. And probably most impressive is that its electric bill was $1,800 per month, and that's in 1946 dollars. When they turned, this was in Philadelphia. When they turned this thing on, Philadelphia dimmed a little bit. So, in fact, what's most impressive, a vacuum tube is like a light bulb. It actually glows. You ever seen one? Who's ever seen a vacuum tube? And for chance, if you ever get an old TV set and look inside it, then you'll see these vacuum tubes. And they're like little light bulbs. What happens if you take a light bulb and go out into the middle of a forest at night? What happens? All the flies and bugs all collect around to it. In fact, this thing, one of its failure modes was the fact that it would attract moths and flies, and they would crawl in and they'd short circuit out the thing. In fact, this is the first bug in a computer. It was a real bug. Okay. So to run this thing, I mean, they were able to actually do computations for the first time that people never could, but it wasn't very good. And so things really changed when people realized that maybe we can make these things smaller. And so here was the real first transistor made in 1947 down the road at Bell Laboratories. And by the next year after the demonstration, they were actually selling these things. They made about 1,000 of these things called Type A transistors. By the way, if you ever run across that, snap it up because it's a huge collector's item. And by 1954, they were making millions of these things. So they were able to actually make transistors that would eventually enable what we have benefited from, the information technology. Now, a modern computer chip that runs your computer or runs your cell phone or runs your iPad has roughly 1 trillion transistors on it. For people familiar with it, 10 to the 9th using exponential notation. So 1 trillion transistors. Now, suppose I had a bucket of these things sitting here. Okay, so I got a bucket of transistors over here. And I'm going to wire them up over here. And I'm going to wire up 1 trillion transistors. And so I take a transistor and I place it on my little breadboard, one every second, 24 hours a day, 7 days a week, 365 days a year. How long would it take me to make the equivalent of one of our integrated circuits? Well, to do the calculation, there's roughly pi times 10 to the 7 seconds in a year, so it would take you 30 years to make one. And you can buy one of these little things for a few tens of dollars. And they're all over the world. So it's an amazing new technology. And that happened because of something called that, again, Jack Kilby, who invented the concept of the integrated circuit, as well as another guy by the name of Robert Noyce, came up with the idea that you can put a lot of things made together all at the same time. And it was an important intellectual concept. So the concept is that you actually use a pattern that you've generated, a mask, that creates patterns on a piece of silicon. But here's the important thing. Instead of taking one at a time and putting them on a breadboard, on your integrated circuit, it makes 2 at the same time, or 10 at the same time, or 1,000 at the same time, or 1 trillion at the same time. So instead of doing the sequential process of doing things like the Ford assembly line, in fact, it's what's called a parallel process. And that concept was so important, it enabled the generation of integrated circuits that we have today. So shortly after the idea of this concept came in, here is one of the first integrated circuits made, and done by Intel. And it had all of what are called 4 bits of information. And if you know anything about a modern computer, that's absolutely nothing. And it only had 2,300 transistors, and it ran at a blazing 110 kilohertz. We now do gigahertz. And it cost about, in $1910, cost about $500. But in fact, it was one of the first integrated circuits. A few years later, they've increased it. They've increased this about a factor of 10. They've increased the speed dramatically, and it costs roughly the same. Today, incredible increase in the information density, incredible increase in the number of transistors that you can make, and it costs roughly the same. So that has been the march and what's called the silicon steamroller, as we're able to make more and more complex things for roughly the same cost. Okay. So here's a pretty picture of what we do today, very complicated integrated circuits. But it's actually not all that complicated. In fact, one of the big secrets that the electrical engineers keep and don't tell anybody is it's simple. So we just don't tell people that. And it's actually very easy to understand how these things all get connected together. So it's a very wonderful, interesting technology, and pretty simple technology. And this increase is something called Moore's law. And what it says is that the number of the number of transistors that we can put on one of these integrated circuits doubles every 2 years. Now, just think about what they mean doubling. It doesn't mean that it increases by a factor of 2. It doubles over what it was before. So 1, 2, 4, 16, et cetera, et cetera. And so the number is increased dramatically. And so now, this is kind of an old graph. It's continuing on to that. And we have billions and billions of transistors that we can put on these. And so that's why the things we have are getting more and more complex, can do wonderful things. Some of the, for example, who saw the latest Star Wars? Right? And you know, a good 80% of that movie was computer generated. And so all the scenes, and you couldn't do that many years ago, and so a lot of the things that we see around us today are due to the wonderful ability to be able to do computations at a blazing speed. Okay. Now, a lot of things follow Moore's law. Here's another thing that follows Moore's law. The number of chickens. So, but that's something called an experience curve for that. It's due to something in economics. So, okay. So we're able to make these tiny, tiny little transistors, very, very small. In fact, here is the size. Here's a typical transistor that we make these days. It's only 45 nanometers. Now remember I said a micron? That's 1,000 nanometers. And now it's that big. So it's tremendously small. Okay. So we can make things really, really tiny. And that's what we do in our laboratories today, is try to shrink transistors and make them really, really tiny. So the question is, if we go back to Moore's law, back here, how much further is that going to go? Is that going to go on forever? Are computers going to start to get better and better and better all the time? And here's something that's really fascinating and you should take attention to. Electronics is going to change dramatically within your lifetime. And it has to. And I'm going to show you why, because this is not going to continue forever. It's actually going to stop. And when that happens, a lot of people are going to go, what do we do next? What's the next possible thing that we can do electronics? So that's what I'm going to talk about today, some of the wild and wonderful things that we think we can do. So why is it stopping? Is it because we can't make the things smaller and smaller and smaller? And so that's what I do part of my research on, is how small can I make these things? So here's a little plot that shows the size of the transistors that we make. And back when Moore guessed that things are going to double every time, we were about this size. By about a decade ago, we were down to here. We are now approximately right here. And we're starting to get incredibly small. So we can make things incredibly small. In fact, I can make things down to a single atom. We've been able to measure the properties of a single atom in our laboratory. So in fact, how small can we go? In fact, no, let me go to this. In our laboratories, we actually made a transistor out of a single molecule. So how tiny is that? That's less than a nanometer in size. And it worked. Now, it took a lot of work to be able to get it that tiny. But nonetheless, that was an important lesson in the fact that size doesn't matter anymore. We can make things incredibly small. So is that going to be the limit of electronics? So it's an important question from both an intellectual standpoint and from an industrial standpoint. From an intellectual standpoint is what is the limits of making a device and what are the properties that determine that? And from an industrial standpoint, they want to know if they can do the next thing so they can invest in the capabilities and the machines to be able to do that. And it's a big investment. So to make a modern Intel clean room to do the modern chips that I was talking about, that I showed you some pictures of, how much do you think that costs? You know, maybe $1 million, right? $5 billion to make a single fabrication facility to make state-of-the-art things. So it's a serious investment from a company standpoint. Okay, so we can make things really small. So we took a little molecule. Does anyone recognize what that is?
Benzene?
It's benzene. It's a single molecule of benzene. And sandwiched between two contacts, and we're able to actually show it was a transistor. And so for some of the people that's actually the transistor curves we got. Don't worry about that. But it actually shows that it works like a transistor. It actually showed worked like the same types of transistors that Bell Labs, the same type of vacuum tube properties that Lee DeForest did, and it was made out of a single molecule. So size doesn't matter anymore. It's how hot you are. That's the real limit of electronics. And it wasn't obvious until about 7, 8 years ago that people really realized that this was the limit of electronics. So if we go back to some of the first serious microprocessors, in fact, my first computer was something that ran on something called an Intel 386 computer. And so that gave off a certain amount of power. Here's in some units, and I'll show you exactly what that means in a second. And this is as we march down in size and pack more and more transistors onto an integrated circuit. And a few years ago, we were working with things called Pentiums, and that was roughly the temperature of a hot plate. Okay? So what do? We made more transistors on an integrated circuit, and we packed more and more on. And now we're at a Pentium 4, and there's a nuclear reactor. And there's a rocket nozzle. And that's the surface of the sun. So in fact, it became something that people started to recognize as going to be the limit of electronics, is that the more transistors you put onto an integrated circuit, the more each one gives off a little bit of heat when it does its computation, and the more energy it's going to give off and power it's going to give off. And this little nuclear reactor point there is a very important point, because the nuclear reactors are built on roughly the limit of what materials can handle. Most materials above that kind of heat will start to degrade and fall apart. So we don't know how to do that. Now, this is affecting you today. You might not know it, but for the last 7 or 8 years, your computers have not increased in performance. What they've done is they've done clever tricks that you haven't seen to be able to make it look like it's performing better. Let me go to this. Okay, now, complicated graph here, but the important thing to notice is, and here's a very simple way to look at it. This is the number of transistors, the green plot, that's increasing. So as time marches on, the number of computers or number of transistors on a chip are following Moore's law. And so we're packing more and more and more in them. That's good. This thing right here, which says the clock speed, has stopped. And it's flattened. And that goes against being able to increase the performance. Because if I put more transistors on an integrated circuit, I want to clock them faster to get the increase in performance. But if I have more transistors on there and I haven't increased how fast they do the computations, well, I've lost the game there. So that's what people are dealing with today. And I'll show you some of the interesting workarounds that some people are thinking about. So, in fact, here is, over the years, that's a log scale, within the last, starting in about 2008 to 2014, and there's different designs, so that's why there are different numbers there, but you can see it pretty much has flattened off. So people are starting to come up with wild ideas to be able to do this. Here's the wildest idea I've ever seen, is they actually take the thing and they plunge it into water to be able to cool the thing down. That actually might happen. And people are coming up with interesting ideas to be able to get around that. Okay, so as people are trying to come up with better ways to be able to increase the performance of that, a whole lot of new ideas have come up. And you're going to see a lot of this in the next few years. Now, the interesting thing is that energy, the fact that these things heat up is not just a problem for the computer, it's a problem for society. In fact, right now, just searches, internet searches, uses 3% of all the global energy that we have. And it's increasing. And I suspect within a year or two, it'll be up to 5%, and it'll continue to increase. So we got to come up with something, because that really translates into greenhouse gases and all the problems we know about energy production. So here is a wonderful little complicated graph that you don't really need to understand of, but you just need to look at some of the names that we have right here. What this is how fast the thing is, how small it is, how much it costs, and the energy that it gives off. And there's all sorts of different types of things that people are trying to think of that are able to get around this problem. For example, you see this right thing. Blue means you've gotten around that. There's things like biologically inspired computation. There is molecular computation, the molecule devices that I was showing you right there. And these things might have much lower power dissipation than what we have right here. There's something called NEMS. I'm going to show you a few examples of these where people are starting to do this, and it's a wonderfully vibrant research area. So if I had to pick a topic in a field of science that had the most incredible ideas and diversity of things, it's the electronics, trying to figure out what it's going to do next. So it's a wonderful thing to think about. Okay, so what are some of these things that we have right here? Well, a lot of these are enabled by the fact that within the last 10 years, scientists have been able to have started to get into a field called nanotechnology that allows us to make things at amazingly small scales, things that are almost inconceivable. Here's just an example to show you these size scales. Here's a typical type of integrated circuit. That kind of gives you an idea of the size scale of what these are with respect to something like a little ant that's sitting here. That's actually a little integrated circuit I made in my laboratory. And a friend of mine was a microscopist, so I said, "Can you put it in his mouth?" And he did. Okay. But we've been able to do things like be able to place single atoms, one at a time, in various places. Here's one of the first experiments. This spells out, can you read it? IBM, right? Done by a guy who did some of the first experiments on showing that you can actually do single atom manipulation with things. This one's kind of interesting because this is in kanji, it spells out atom. So. And we can make mechanical things too. Here's a tiny little guitar. Made up the road at a place called Cornell Nanofabrication Facility. And you can see it's a nice little Fender guitar. You can see the actual strings that it has right there. It actually plays notes. It does, except they're at gigahertz frequencies. You can't hear them. But in fact, we actually have a guy down the road, Hong Tang, who actually makes things like this and is able to sense the various types of vibrations that happen in very small systems like that. So there's all sorts of interesting new technologies that are happening. In fact, one of the oldest technologies in the world of being able to do this has been revived, and it's something that are called quantum dots. Now, in fact, these things right here have all sorts of applications, and they're in your life today, and you don't even know it. Who's seen some of who's ever bought one of these new LED light bulbs, right? Some of those have quantum dots in it that make them more efficient. So these are used for all sorts of medical purposes. Here's an example of a little rat that has a little tumor there, and you're actually able to image the tumor using these things called quantum dots. And what they are is tiny little assemblies of just tiny little packets of atoms. Very, 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 very tiny. Actually, there's an interesting thing. It was actually invented back in 1480, although they didn't know it. In fact, all these beautiful colored glasses that were invented around in that time frame How did they do that? People would take glass that was perfectly clear, and then they'd add a little bit of gold, or they'd add a little bit of copper. And if they cooled it just right, then it would have, in fact, this thing that you see right here, which is called rose glass, is when you take gold and you would add it to the melting glass and then cool it down at a certain rate. In fact, if you didn't cool it down at a certain rate, it would turn into something that looked like mud. But if you did it just right, it turned out to have this beautiful color. They didn't know why. Actually, what they were doing is they were creating these little quantum dots in the glass, and it gave it this nice color, and the various types of colors that you see right here. So it's a wonderful little new technology, reinvented now to be able to do all sorts of interesting things. So all these new materials and all these new fabrication processes that people have been exploring for the last few years has opened up all sorts of new opportunities. One of the most interesting things is something called MEMS, micro-electro-mechanical systems, to make things like gears and motors on a very, very tiny length scale. So here's a little rotating gear, 50 microns. It's about the size of, again, a human hair. Here's a little thing that does some optics. There's a little switch here. Here is something by a group at Sandia that makes little rotating machines for various applications. And I'll show you an example of one of this. Here's a little movie I'm going to show you that has one of these little rotating gears, and it's got a little bug on it. And so he's getting a little ride. But it shows you. And the reason I do this is that little ratchet gear right there. If you've ever looked at an old clock, an old mechanical clock, which has a little piston that goes back and forth, something called a ratchet. This actually is ratcheting at incredibly high speeds so that they can precisely determine and move this thing with tremendous interesting things. Now, one of the interesting things is that when you're on a very small size scale, your intuition kind of violates, or your intuition doesn't really tell you what's going on. Here's a little bug at a very high speed. He's able to grab onto the thing. He's getting a real ride. Actually, one of the very interesting things, when things get down to a very small size scale, things become very sticky. So he doesn't have any trouble hanging on to the thing. You would, because you're so big. In fact, that's why things like geckos and flies can climb walls, because their surfaces are very small and you get sticky things. Okay, so this whole area of micro-electro-mechanical systems are, in fact, not just doing gears and motors, but people are thinking back. Can I make something like the Babbage machine out of things that are very, very tiny? Can I do mechanical computation, and does that help me being able to solve this energy problem? And so that's a very big, active area of research that people all around the world are thinking about these days. In fact, some of the really interesting things that people are doing, and a huge big area of research, is trying to blend biology with electronics. Now, who's had a class and heard about DNA, right? And you know that DNA sticks together because of these base pairs that you have on the different sides, right? So when you line up DNA, then you have that one of these nucleic acids binds to the other nucleic acid, but not the other ones. And so when DNA forms, it is A binding to T and C binding to G, et cetera, et cetera. And so that's what forms DNA. Now here's an example where someone came up with an idea, and it was a guy by the name of Ned Seaman. He said, forget about biology as far as life. Because I can get things that bind on a very small length scale, preferentially, can I make things mechanical out of them? So what he did is he said, okay, I'm going to take DNA and I'm going to make it fold back and forth and back and forth and back and forth like that, because I can design in the rules to be able to make it do that. And so that should be like a little sheet of paper. And in fact, that's what it looks like. He made a tiny little sheet of DNA paper. There it's a little bit wrinkled. So he was showing the fact it wasn't so stable, but in fact he could. But I can make more than sheets of paper. I can actually design in all sorts of patterns that I want to be able to do interesting things. So here's another example. He made a little star out of it. By being able to program in all the various types of binding things to be able to do that, beautiful little star. And how big is this thing? This thing, that little scale bar that you see there, that's about 10 microns. So very small. This one I love, right there. And it's really interesting. So here's a whole group of them. It's not totally perfect. You know, you can see some of them. That one is pretty good, but this one is like he's screaming, you know. But it's a really new, interesting technology that we think about. And so, in fact, a lot of people around the world are looking at this as a possible way to be able to fabricate integrated circuits. In fact, on a much smaller size, or excuse me, much less expensive, and wouldn't have to use all those billion-dollar fabrication facilities. Okay. There's a map of the world. Shrunk down to something that is about 20 microns across. So it's really phenomenal stuff. So it's called DNA origami. Okay. Yes?
What DNA? Where did you get the DNA?
So where did you get the DNA? Actually, for how people make DNA is what they'll do is they will take one of the base pairs, or just imagine you had a little string of DNA and they want to add something to the end. So what they do is they put a little group on the end where preferentially one is going to come in and substitute, and then the other one goes away. And that one has another preferential and it comes in and substitutes. So you can make a string of DNA with a programmed sequence. And in fact, you don't need a laboratory to do it. You can go out and you can order it on the web. And it'll cost you about $50 or so with a tiny little vial like this, and it'll come back and you'll have precisely that programmed sequence that you want, because there are many companies that do this for a living. And they do things like gene sequencing and various types of things for biomedical applications. But this isn't biomedical, it's actually structural. But it uses the same type of thing. Okay. Now, there's a lot of different stuff going on in electronics these days. And let me just give you one example of the way electronics affects your life. And there's a whole area of what's called 3-5 materials, not silicon, but other types of materials that people do for what are called optoelectronic and radio frequency applications. An example is this thing, which is a laser. It's precisely what I'm pointing around right there. This little thing right here is a result of the research over the last 20 years to be able to not just have a laser pointer, but this is used for telecommunications. So the fact that you can have such high speeds are due to the fact that lasers are going over fiber optics to be able to do high speed information. But it does things like very efficient solar cells. Solar power people talk about today. And it's an ongoing debate, and people are trying to see if it's going to be cost effective. But in fact, these things right here are incredibly high performance things, solar cells made out of these new materials. In fact, a typical solar cell has an efficiency of approximately 17 to 18% made out of, that's the one that you can buy that you put onto your roof. This one is about 50%. Now, it costs about $1 billion. Well, up in space, you really need that. So there are certain applications where that efficiency is very important. Modern radar systems. Here's a picture of a modern radar system. Use these different types of materials to do that. Anytime you look at Intellicast or whatever your favorite weather app is, then the radar maps that you see there, the storms moving through, are due to the fact that we have such incredibly efficient radar systems these days. If you have a cell phone, you have one of these things. And in fact, the ability of being able to make these very fast radio frequency transistors relatively cheaply these days allows enable the entire cellular communication system that we have. But these are examples of the various types of things, but the one I want to concentrate is on this, which is displays and lighting. And it's actually had a tremendous impact. So we're all familiar with light-emitting diodes. If you have, a little camcorder or something like that, you see flashing red light bulbs or flashing green LEDs. If you combine red, green, and blue, and this is the amazing thing that happened within the last decade, is people were able to get the color blue. In fact, a group of people won the Nobel Prize a number of years ago, being able to actually create blue light. You combine red, green, blue, and what do you get? You get white. Now, big deal. I've just done something a little bit differently to be able to get white light. Well, the point is that it's amazingly efficient. So these light bulbs right here, how efficient are they as producing light that comes down to us versus the power that we put in? Well, this one right here, which they should get rid of, is an incandescent light bulb. And, well, there are some incandescents here. Oh, yeah, that's right. That's an LED. Yeah, you actually did replace them. Excellent. The lights that you have at home, the old style lights that give off the warm glow, those are called incandescent light bulbs. And they have an efficiency of approximately 10%. In fact, there's some they say this has a much warmer glow to the thing. It's actually, those are worse. That's about 8% efficient. Right? The lights that are probably behind those, which are probably fluorescent lights, are on the order of 15 to 17% efficient. Okay, so that's better. That's why people put in fluorescent light bulbs. And there are some that are called high power fluorescent light bulbs that get up to about 20 to 22%. These things have an internal efficiency of 99.9999%. Amazing. In fact, it turns out it's a really interesting optical problem, is that the efficiency for light out is actually trying to get the light out of the thing. In fact, it's like a diamond in reverse. You can't get the light out fast enough to be able to, it bounces around inside. And people are working on that, so they've gotten up to about 55 to 60% efficiency on these things. These things right here here is their efficiency as a function of year, here's the best LED, which is beat out all these other things like fluorescents and halogens and high pressure sodium and all these kind of things. So right now, the best LEDs that you can buy on the market are roughly the same as the high pressure fluorescents, which are on the order of about 22% or so. However, the LEDs are getting better and better and better, and this year they've just crossed over. And within the next 5 years, they're going to get up to about 30 to 35%. And hopefully we'll get all the way up to 50% or so. In fact, the reason that these work actually better and more efficient is because of these quantum dots that I told you before. That's billions of barrels of oil that you've saved. So in fact, this tiny little electronic innovation has affected worldwide global energy dramatically. So the lesson is, I know they're expensive, but buy the LED lights. They really save the world, and they actually save cost to you in the end because they last a very, very long time. Okay. I'm sorry, that little graph right there, there's a little figure that you might not have ever thought about. How much energy in the world do we actually use for lighting? And in fact, that's 30% of electricity is actually used for lighting things. That's a lot. That's a tremendous amount. And increasing this efficiency is a very important thing. If you look at all the energy that the United States uses, and here's all these various numbers of where it comes from, where it goes, the only number that's really important there is that's the amount of electrical energy that is lost. 30% of our electrical energy is lost due to the fact that we have inefficient lighting and various types of things. So we are going to dramatically change that with this. Okay. Now, let's come back to some of the other ideas that people are thinking about. There's a big area of research. In fact, Yale is one of the leaders in it, doing what's called quantum computation. Now, what is quantum computation? Transistors that we know use bits of information, a 1 and a 0. Quantum computation uses things that are not a 1, not a 0, it's somewhere in between. And the way these things actually do computation is using quantum mechanics. And it's a very, very researchy thing. This is the biggest quantum computer that people have ever made, 1, 2, 3, 4, 5, 6, 7, 8 bits of information. But people are doing experiments on that now. And so over the next few years, you're going to start to see a lot of interesting news articles on being able to do more and more efficient quantum computers. Why is that important? It uses a whole lot less energy. And so that potentially is an idea that people have to get around the energy problem of computation. And being able to do these quantum type things, you can actually see quantum effects. These little fringes and ripples and stuff like that are due to the quantum effects that you see when you make one of these little structures, things that are called wave functions. So someday down the road, you actually might get into a class and read something on quantum mechanics. And the fascinating thing is that today we actually play around with quantum mechanics. We design things with quantum mechanics. However, here's what I think the future of computation is, which is different from those other people. So not that the other people are wrong. They have their ideas. They're exploring that. But I actually think the blend of biological systems with electronics is going to be one of the most important things that's going to happen over the next few years. And the reason I think about that is it addresses the underlying fundamental problem of energy. Now, what are we doing today? Do we have things that blend electronics with biological? Do we have a cyborg? Do we have a Terminator and things like that? No, we're far, far away from that. In fact, some of the first things that we're doing right here is just making electronic systems that can sense what's going on in the world around us. And in fact, this is the research that I do in my laboratory. I make little systems like this that has an integrated circuit underneath it to be able to sense things that exist in the world around it. In fact, this was an example of sensing a certain type of molecule that is indicative of breast cancer. And I can do this at incredibly small, sensitive levels. And I can measure who's had a chemistry class? Huh? Who knows what a molar concentration is, right? So what happens if you take something and a certain number of atoms and I put it into a liquid, then I have a certain concentration. If I take 1 mole, I put it into 1 liter, that's called a mole, or a molar concentration. The bottom, even if you haven't had the chemistry class, is the smaller the concentration, the less molecules there are. So for example, if I go and I do a test using something you can buy in the store that is to measure the amount of insulin and glucose you have in your system, then you can measure that at roughly micromolar concentrations. Our new systems like this can measure it at femtomolar concentrations, incredibly small concentrations. And I'll give you an example of how small that is. 1,000 bigger is what's called a picomolar concentration. If I would take a grain of salt and I would put it into an Olympic swimming pool, that's a picomolar concentration. And we can measure less than that. So these are the kind of amazing sensitivities that we can get out of these things. So this kind of research is just beginning for us to sense the world around us. Eventually we're going to make electronics out of this. But the reason that we're thinking about biology as a potential way to get around the energy problem is the following. The whole last century of making integrated circuits was using wires that connects those all together. Copper wires that connects one transistor to another transistor to another transistor. And that's what causes this heat problem. But there's an existence proof on how to do it better. Okay. So here's what we make today. We have 1 billion transistors, operates at very high speed. That's about 100 watts, and each of these tiny transistors is about 30 nanometers. The existence proof that we can do it better is this, right? It's got 10 to the 14th synapses. It's got a whole lot more. So why doesn't your head burn up? It only operates at about 20 watts for most people. But actually, this is like the picture I showed you before. It's immersed liquid. So in fact, the important thing is that you evolved constrained by low power. Right? You're a low power system. Because if you're a higher power, you'd have to eat more food and you wouldn't survive. So in fact, you evolved to do computation at low power. That was your constraint. We didn't have this constraint for that. We just put the pedal to the metal and did it as fast as we could. But then all of a sudden we've realized the problem that we have with that. So we're going to start to make things that look more like this, and we're starting to do the basics of the research to be able to do that. Are you going to see a brain like this within your lifetime? Probably not. But you're going to see the beginnings of the research to be able to do that. And it's very important because it does computation in a much different way. And let me give you an example. So you're here at Yale in a classroom. I get to give you a test. Okay? Now, if you know the answer to the test, don't yell it out, okay? Just raise your hand or something like that. Okay. I'm going to show you a little picture. Oh, I'll come back to that. There's a little picture. Now, a computer recognized this within about 10 milliseconds. Okay? You haven't recognized it yet. Okay. Let me show you a little more. Okay. Took about 100 milliseconds, almost a second for the computer to recognize this. Okay. Now, see how long it takes, how fast it takes you to do this. A computer is still working on it, and it'll take about a minute. Because it does computation in a much different way. So being able to not only do low power computation and computation in the different way that brains operate from the way that we've done transistors is what the future of electronics is, to figure out the difference between here so that we can get around this problem of energy consumption. Thank you very much.
Sure, Professor Ree would be happy to answer questions. I know I've got one. So your last example, that's really pretty cool, thinking that the human brain is going to do better at computation. So it's not just as doing in biology, though, right? So you, instead of having that many more transistors, it just had a hell of a lot more interconnects. So if anyone tried to engineer and make that hell of a lot more interconnects with slower devices to simulate a brain and see if you actually can, go down that path.
Right. Yes, they have. So the way that we think about modern electronics is that we connect one transistor to another transistor to another transistor, kind of like a switching network. Now, what we do is we have one input, one output. One input, maybe two inputs, one output, two inputs, one output, two inputs, one output. That's the way we put transistors together, and that's the way we've always done it, and we don't know how to do anything else. This thing, every single synapse and axon is connected to maybe 1,000 or 10,000 other ones. So it's very, very complicated way that these are all connected together. So in fact, people have come up with the first ideas, things that are called neural networks. And those are actually realized in actual devices to be able to do things like pattern recognition. And you know what? It did. They were able to actually recognize patterns much faster than the way that people would do it. Now, we're still at the very beginnings of understand how to connect up those things with the neural networks and the various types of rules where the things are connected and how things feed back. So we still have a long way to learn in that. But at least there's an existence proof that it works differently, and it works not like the things on the left, but a little more like the things on the right. And so there's a whole big area of electronics looking at, oh, maybe this, and they call it biomorphic type of integration of circuits, of architecture, and of software. We don't understand the software over here. That is Windows or something like that. And you know how clunky that is. And that crashes every once in a while. Well, that crashes once in a while too. But in fact, the interesting thing is that that is not just electrical. It's actually very chemical too. So all the electronics and the chemistry coming in together. In fact, we haven't been able to address that onto electronic devices. And in fact, that's an area of research I'm trying to get into. Yeah.
Hi. The brain you show in the current state, can it do 10 to the power 14 synapses?
Oh, that's how many synapses it has.
The state you are showing here, it's connected from the human body.
Yeah.
Can it do it in this state?
No.
So what if you tap into something which powers the human body? What could you do?
Yeah. So in fact, there's two areas of interest here. Is can you use and tap into the brain or the human body to do things? One of the interesting things that people are thinking about from tapping into the human body, not the brain, just the body, is to use the energy generation cycle, what's called the ATP cycle, that we have in our system to actually power electronics. And some people have actually demonstrated some circuitry to be able to do that. It's not very good yet. Hopefully it's going to get better than that. Being able to use electronics to tap into this is just at its very beginning. So I think that's kind of complicated. In fact, my area, I want to, instead of tapping into a brain like that, of which 10 to the 14th, I don't know how to control that. But in fact, there's this little worm called a C. elegans. It's got about 300 synapses. I think I can tap into that. So I'm going to start right there on understanding simple systems to be able to then generalize to that. So are we going to be able to tap into that and understand how it's thinking? Well, I think we're going to someday, but it's a long road. Yeah.
Do you foresee electronics and nanotechnology one day replacing chemistry in addressing human disease and replacing medicine?
So I'm standing in a chemistry building with another chemistry professor over here. They complement each other. So in fact, the electronics that you see there is kind of a blend of chemistry and of electronics together. So right now, the way that we do things like quantitative analysis for chemistry, we have a lot of good sophisticated tools, of which this guy is one of the leaders of. But the electronics has only been kind of the computers to run all that stuff. And over the last few years, people have started to get the electronics into the sensing system to be able to actually do that. And in some applications it's good, some applications it's bad. So there's a blend of various types of electronics that we can be able to do. I think you're going to see within 5 years, because in fact I'm working with a company that's doing this, you're going to have something in your hand to be able to say whether or not you have malaria. Or whether or not you have a certain breast cancer marker in you. So you're going to see portable electronics. I mean, right now, what is wearable electronics? You know, it's a little accelerometer. It tells you how fast, you know, how much you moved. That's all it is. But at some stage, it's actually going to read your sweat and tell you whether or not that you should maybe go in and see the doctor. For example, here's a great example, is that there are some people that have to take a certain well-defined amount of medicine every day or every week or something like that to be able to stabilize their hormones or certain proteins in their blood. And in fact, the sad situation is most of those people don't do it correctly. and they end up having serious diseases as a result. For example, there's a chronic heart disease where you have to take a daily dose of something to be able to do that. If you could actually measure those things, and now they actually have to run into the doctor's office and get a blood test, and that's, you know, they get tired of that after a while, then eventually you'll be able to do it yourself and be able to see that everything is good. It might be too much information, you know, you might say, don't eat that steak. But I think that's the future of where this is going, yeah.
When you were plotting the Moore's law curve,
Yeah.
how would that map out if we were looking at the biological system and the synapses? They're an evolutionary process.
Well, I mean, what we could do is, we don't have a knob that we can turn there as far as, okay, I have a brain that only thinks this much and let's increase and stuff. And when you cross species, there's a bunch of other things. However, there is another plot that's very important, and that is this one right here that I skipped over because it had a lot of information. But here's the important thing. This is how fast things switch, what their power dissipation is. And these lines simply say all your things are on the same amount of energy. So lines like this are constant energy. Over the years, our electronics has gotten better and better and better and better, and this is pretty much the limit of what we can do due to some things. And what happens is I go up this, and I go up this, and I go up this, and the synapse is right there. So in fact, that's what's motivated me to do this, is that synapses work very slow. I mean, this only operates at a few tens of hertz. But it does it incredibly efficiently. So that's why I think the biological computation, which evolved on low power, is the important thing. Now, how has evolution, how is if you take things and increase 10 to the 15th or 10 to the 16th or 10 to the 17th synapses, does it compute better? We don't know yet. I think fundamental understanding will realize if there are certain limits to how big these biological computation systems could be. That's a great, interesting question. Yeah?
One last question. So you were saying Moore's law of computer speed started to really flatten off. So when are we going to see the next big increase in computer speed, and what will it be?
When will we see the next increase in computer speeds? There are two answers to that. Number one is my answer, which says that never. However, with the caveat, is that people are looking at some of these alternative computational type devices and structures. And right now, the research is just very young, very beginning. A lot of it isn't working very well, but that's why you do research. If one of those actually comes in and hits a home run, we might actually see that. But in the absence of that, I don't think we're going to see that, is clocking speeds and the... Now, how have we gotten out additional performance? Well, what's happened is finally the software engineers had to go back and say, oh, I got to get to work and make it more efficient. So what they're doing is, and here's an interesting thing, is little story. When I was growing up, my dad would get absolutely furious at me if I would walk out of the room and leave the lights on. It says, you know, we aren't Rockefeller, shut the lights off. Now, a big computer chip, like the one I showed you right here, you know, the way we design them is everything is always on in computing. Well, in fact, some of the latest generations of computer chips, when you aren't actually doing the computation, they shut everything off. And then they run over, they do this computation, and I got the answer for that. I'm going to run over here. I'm going to shut that off and turn this back on again. So it's actually shutting the lights on and off in the room. And they've actually gotten better performance out of it. So clock speeds haven't changed. The number of transistors haven't changed. They say change the software on how things go. So we're going to start to see software innovations over the next few years to be able to increase the performance. But the whole bottom line is it's eventually going to do that. So that's why I say electronics is going to dramatically change within your lifetime. It's either going to slow down and saturate, or there's going to be, and that's what I think is going to happen, there are going to be some new tremendous innovations that are going to happen. And that's the fun of research. Okay.